Okay, off we go. So picking up where we left off last time, we had talked about the fundamental theorem of line integrals. Here's a related idea. The book actually introduces this idea first. And there's always trade-offs when you talk about what order to present ideas. I kind of personally prefer the trade-offs doing this after the fundamental theorem of line integrals, but whatever. Anyway, so here's an uncontroversial statement. If you're going to do a line integral on some curve, it depends pretty significantly on the curve. Well, of course it does, right? I mean, the curve is where you're evaluating the vector field. Its direction is wrapped up inside of what the dx vector is. Everything in this computation depends very strongly on what curve are you talking about? So what's really surprising is that it turns out that for some vector fields, it actually doesn't matter so much. And this is, I think, quite shocking. There are some vector fields, what we call vector fields with path-independent line integrals. Or to be totally honest, I prefer this more streamlined terminology here. A vector field is what we call path-independent if it has the following property, and that is that if you have two curves, any two curves as long as they start at the same point and end at the same point, and start has to match up with start and end has to match up with end, right? They can't sort of go opposite directions, as it were. Any two curves that have the same starting point and same ending point will share the value of the line integral. So the green line integral and the blue line integral, always the same. Now I emphasize this is a very surprising thing to claim, and I emphasize even more strongly, this is not always true. This is not a generic statement, right? This is specifically for these very special, what we call path-independent vector fields. So again, not claiming that only the endpoints matter in general. That is absolutely false. What's still surprising to me is that there could possibly exist any vector field. You kind of think about it. How could there be a vector field where the curve doesn't matter in between a fixed starting point and a fixed ending point? Now, what's the intuition here? Well, because this blue line integral, look, it's way over here. It's super far away from this green curve. So, if I were to go further in this direction, I'd be getting into parts of the vector field that are completely unrelated to the parts of the vector field I'm looking at over here for the green integral. It just seems implausible that somehow the curve doesn't matter. Now, just to underscore how improbable this seems, and again, I emphasize, most vector fields do not have this property. Right? This is a rare property. So again, easy sort of intuitive counterexample. Let's consider two curves that start at this point, that end at this point. Right? They both have the same start and the same end. Let's think about this one here that goes like that, like I have highlighted in green there. And, the vector field is 0 over there, so there's no line integral on that sort of leg, if you will. And the vector field is perpendicular to the curve over there. So the dot product, if you think about how vector line integrals work, it's vector field dot dx, right? Well, the vector field's like this. Dx on this top part of the curve is like that. That dot product is 0 because they're perpendicular. Right? So that part of the integral is 0. So altogether then, on this green curve, it's pretty clear that green line integral is 0. Whereas, now just for contrast purposes, let's compute on C2. Well, there's that leg right there. Again, everything's perpendicular. There's no line integral on that leg. The vector field's up. The dx is to the right. Orthogonal means Dot product is 0. But then you look on this leg right here. On that leg, we're clearly going to have positive line integral. Again, another interpretation of a vector line integral. To what extent is the flow of the vector field along the curve? Well, check it out. It's quite significant and clearly in the same direction the curve is going along this curve. So on the green curve, we clearly get 0, but on this blue curve, we clearly get positive, aka not 0, right? So this is the what I'm going to call the intuitive sort of counterexample. This is what you would expect to happen. Different curves, different line integrals, of course. And again, I emphasize, so with concerns like this in mind, it's hard to imagine how any vector field could have this property of being path independent. Okay, so let's obviously, I wouldn't define something only to eventually show that it doesn't exist. That would be kind of silly, right? So obviously, I'm going to show you that there are some path independent vector fields. And in fact, not only are there some, there's a bunch of them. In fact, every gradient is path independent. Every gradient. There's a little asterisk we have to put on this. There are some nasty little sticky wickets that come up if your vector field fails to be defined so much as at any single point. You do need to require for these, for our purposes here in this course anyway, that every vector field that we're going to discuss is going to be defined everywhere. There will be a couple of sort of counterexamples to this that we'll talk about later, but that's going to be very much a later thing. So when I say gradient, I mean that the vector field is the gradient of a function everywhere in our domain, no exceptions, and furthermore, everything's continuous. We need a certain amount of niceness. Okay, so I claim that this is a path-independent vector field. And here's the argument. Now, keeping in mind, path-independent does require that we only look at curves that start at the same point and end at the same point. And I'm going to entertain first moving along that green curve, and then next moving along this blue curve. Same start, same end. Right? And now let's think about how would I evaluate this green line integral here. I claim I can evaluate with this formula. Wait a minute, where'd that come from? What gives me the right to compute this green vector line integral with seemingly the fundamental theorem of line integrals? Well, because by assumption, our vector field is literally a gradient. So the fact that our vector field is a gradient means that I can compute the green line integral with the fundamental theorem, and the fundamental theorem only looks at the starting point and the ending point. It looks at A, it looks at B, doesn't look at anything else. Right, and then likewise, let's think about this blue line integral here, moving along C2. Well, again, my integrand here, my vector field, still a gradient. So this is not just a random vector line integral, this is a vector line integral of a gradient. We compute with the anti-gradient. We compute with the fundamental theorem of line integrals. So, why do we get the same answer for these two line integrals? Well, because the fundamental theorem computes both of them looking at the same starting and ending points. So, that's the big idea. This demonstrates for us that every gradient is path independent. So, not only does path independence happen, it happens a lot. Everybody good? That makes sense? Now, what is a little bit harder to prove, and I'm going to say not exactly what we're here for in this course, is that this goes the other way as well. Not only is every gradient path independent, but in the, again, restricted category of continuity and no singularities, no weird issues. Furthermore, every path independent is a gradient. In other words, gradients are the only path-independent vector fields, regularity issues aside. So again, I'm not going to prove this. If you want to sort of think about that on your own, here's a quick sketch of the proof, and feel free to take a look at that and think about it, and maybe try to work it out. If you have any questions, of course, as always, please come to office hours. I'll be happy to help you walk you through it. But you don't need to. This is not part of the course, really. Okay, now here's a different way to say path independence. Now, first of all, let me remind you, path independence says if I have a starting point and an ending point, and if I have two curves over which I'm looking at vector line integrals that start and end at those same points, then I need for the green to equal to the blue. That's what we mean by path independent. I will point out that green equals blue is equivalent to the statement green minus blue equals 0, right? Nothing happened there. That's exactly the same statement. Subtraction is the only thing that happened there. And now for a moment, let's think about what's going on with, let's see here, I need a color choice. How about, I'll use this one. Let's think about this difference. Integral along C1 followed by, now you're going to be tempted to say integral along C2, but keep in mind this minus sign, and don't forget a minus sign you can think of as meaning that you're moving the wrong direction along C2. So you can think of this difference as representing the following curve where you move along C1, and then when you're done with that, you move backwards along C2. Like so. And so saying that this difference is 0 is synonymous with saying that this closed line integral over that combined curve that I'm calling C must be 0. How are we doing? Everybody all right? So getting rid of all this previous stuff, if I can get my pen to cooperate, let's get rid of all of that. We don't need all that anymore. What we have now is a new formulation of path independence. A vector field is path independent if, as it says right here, closed, you see right there, closed, starting and ending at the same point, closed line integrals must all be 0. Just a different way to say path independence. There are some circumstances in which this, where did it go? This point of view here about two different curves, same start and end points, integrals must be the same. This point of view is really useful in some cases. On the other hand, this point of view is really useful in other cases, right? So it's important to be familiar with both of these definitions, sort of all competing but equivalent definitions. All right, so let me show you one place that this comes up nicely. I don't know if y'all are familiar with the work of this artist named M.C. Escher. He did a bunch of, I'm going to say, artistic illusions, kind of, among other things. And here's an example. The name of this artwork escapes me at the moment, but the idea is it shows a bunch of guys walking, sort of following each other on some stairs, which doesn't look particularly concerning until you sort of realize that they're always, these people on the outside seem to always be walking uphill. That's weird, right? And you think for a second, wait a minute, you can't go around in a circle going uphill the whole time. That doesn't compute, right? And then likewise, you look at the people on the inside, and well, they seem to be going downstairs. Again, the whole way around the loop, it just doesn't make any sense. So what we're going to do here is use this idea of path independence to, I'm going to say, at least give a mathematical sort of expression of what our intuition tells us as, come on, that's a bunch of nonsense. Okay, so here's the idea. I'm going to describe what I call the steepness vector field. It's just the gradient of the altitude function. So let's think, what do we know about gradients? Well, gradients point in the direction of fastest increase. In other words, gradients point uphill, right? And their magnitude tells you how steep. So in some sense, this, what I'm calling F here, this points in the direction of uphill, and its magnitude tells you how steep it is uphill. So thus the steepness name that I put on it. So, a couple of really easy observations. Immediate observations. It's a gradient. We know that means that it's path independent. We know that path independent means that closed line integrals are all zero. And now let's take a gander at this right here. What's going on here? What does this vector line integral represent? Well, f is a gradient, dx is a displacement. Each term in this integral, each term in the summation, f dot dx, is representing an altitude gain. Right? We're adding up how much all those altitude gains are. Right? So the theorem here tells us that the sum of our altitude gains has to be zero. Right? But looking at the art here, the art would suggest that the sum of my altitude gains, well, if all of my altitude gains are positive as I go clockwise around this staircase, if all those altitude gains independently are positive, that would suggest the sum of those altitude gains would be positive, but it can't be because it has to be zero. So altogether, I mean, again, this was, the writing down the math of this was just a couple of trivial observations based on path independence, and the punchline is that we have a kind of a mathematical expression of why this art is garbage. A garbage representation of reality. It's cool art. I like the art, right? I'm all for the art, but it's unrepresentative of reality. Does that make sense? Okay. All right. Okay. Let's see here. Moving along. So why do we care about path independence? And there's some really good reasons. For one thing, whenever something is surprising but true, mathematicians like it, right? That's what we find fun. So there's that, right? It also is the case that things that are surprising and yet true tend to be useful in a lot of circumstances. I'm going to point out that path independence is actually really, really useful in, for example, a particular situation in physics. And I'm going to be very brief about this because it's not a physics class, and we got to kind of keep things moving here. Y'all are probably aware of this idea of potential energy. Right? If you don't know physics, don't worry about it. This is just an aside. So, okay, there's potential energy. There's also this thing called kinetic energy, and you may be aware of a related notion called conservation of energy, not in an ecological sense, right? But if you lose potential energy, then you pick up speed and therefore gain kinetic energy, and the total kinetic plus potential is always conserved. Right? We call this conservation of energy. Okay, well, wait a minute. Well, what is potential energy? You can't talk about conservation of energy if you don't have a notion of potential energy. So what is potential energy? Well, potential energy is the amount of work that it takes to move from some starting point up to some other point. Right? Okay, well, how much work does it take to get from here to here? How would I define how much work it takes? Well, I would connect them by a curve and then literally compute the amount of work it takes to move along that curve. Which brings up the natural question, which curve, and shouldn't it make a difference which curve I take? I mean, if I take a kind of an arced curve, right, maybe that gives me a different value for work than if I take a differently arced curve, versus if I kind of take a spirally curve or something like that. Shouldn't the curve matter? Well, this is a nasty concern, very serious concern, and you can't proceed with a definition of potential energy until you make the observation that the vector field for those integrals is path independent. And because it's path independent, I can say, yeah, pick any curve you want. It doesn't matter. Just any curve you like. Whatever's the most easy for you, I guess. Whatever. Doesn't matter. right? So path independence is an essential idea in building up the ideas that are necessary to even be able to talk about conservation of energy, right, in physics. You can't even have that conversation. You can't even talk about that as an idea without this idea of path independence. Right? So, and of course, I think any of y'all who've had a mechanics class know that conservation of energy is really important in mechanics computations. And so, again, very, very important. Thank you, path independence, for allowing us to have that. So, so it's I'm going to say useful conceptually more than computationally. Now, here's kind of my pitch against the utility of path independence. If your vector field's path independent, then it's a gradient, as we previously discussed. If it's a gradient, you can use the fundamental theorem of line integrals, which is awesome. Right? So what we have is path independence. Any situation where I can use path independence, the fundamental theorem of line integrals is on the table and applicable. And so why not just use the fundamental theorem of line integrals? Okay. So in some sense, path independence addresses a computational situation that we've already solved. So who cares? Nevertheless, sometimes the fundamental theorem is awkward to work with. For example, sometimes, of course, you're going to need to find that you're going to need to find the little f. So you're going to need to sort of anti-gradient the vector field to see what the f is, and sometimes that can be hard. At which point, path independence can be a useful alternative. So here's an example. Now, this vector field is not hard to find an anti-gradient of. You could probably look at this and think cleverly. Channel your inner crafty, strategy-oriented mindset, and you could probably come up with what the anti-gradient is there. But let's pretend that we couldn't, as will certainly be the case sometimes. So pretending that we can't, suppose we're given that this is a path-independent vector field, and I'll come back to how we might have such a piece of information pretty soon. But if you know that the vector field is path independent, and if the question is to compute this line integral on that curve right there, right, how would I do that computation? And of course, the brute force way to do it is parameterize that curve, sines and cosines. Now I've got integrals that are just loaded with sines and cosines, and all else being equal, I'd kind of prefer not to. So what I'm going to do instead is point out that, look, as long as I tie down the starting and ending points, as long as I don't change those, I can pick whatever curve I want. I could choose that curve, for example. Right? Because I have that the vector field is path independent. That means that I can switch. I can say phooey on the blue curve. I'm going to use the green curve instead. It's got the same start and end. Path independence tells us that those two curves therefore give me the same line integral. I think I'll do this computation on the green curve instead of the blue curve. Does that make sense to everybody? Just citing path independence. Yeah. Mm-hmm.
And you can only do that because you know that the vector field is path independent.
That's right, because it's given to be path independent. And then, now that is a reasonable strategic question would be, what scenario is it that I'm just given path independence, and it turns out that actually is going to happen later in this lecture. Yeah. Okay, so am I going to actually take that actual green curve right there? No, I'm going to take a different new curve, and let's see here. Let me make them more visible here. I'm going to take this green curve C2 down here. Now again, path independence says I can pick whatever alternate curve I want. It doesn't matter. As long as it has the same start and same end, go crazy. So I'm going to do what I think is a good general rule of thumb for all situations. Try to make life easy as much as possible, right? You get to pick any curve you want. Pick the easiest one, of course, right? And I like this curve C2 because it's a straight line. Straight lines are, well, they're just nice in a lot of ways. Okay. So, so at this point, I get to just say, you know what, forget about all this blue over here. I don't need that blue curve. We're done with the blue curve. Now, I'm only interested in C2. C2 is easy to parameterize. It's right there along the x-axis. Y is obviously 0 everywhere on that curve. Which, by the way, the fact that y is 0, let's see here, let me do it like this. The fact that y is 0 tells me immediately that the first coordinate of the vector field is going to be 0 for the purposes of this integral. Right? That's awesome. Lucky break. This is one of the perks of making a nice, convenient choice of your new curve, is you get algebraic goodies like this, right? Y is straight up, flat, 0. Plug that in, boom. Right? Secondly, notice that y, in addition to being 0, y also never changes. Right? Notice that as I move along the curve, I always move exactly horizontally. And if y never changes, that means that dy is 0. Again, gotta love it. Part of the reason why I chose a nice, straight, flat, convenient curve, right? And so the initial question that I was asked, what it boils down to then is computing this line integral. Notice that dot product's immediately 0, therefore this integral is 0, and we're done. We walk away. I didn't have to really do hardly any actual work at all, right? Just make a clever use of path independence and a clever choice of a new replacement curve. Everybody happy with that? Yeah.
So, why couldn't you just say, okay, it's a closed loop? And
but it wasn't. Yeah. No, that's a great question, and I know I interrupted, but let me see if I can persuade you with this. So my initial curve here, the top half of the unit circle, my initial curve was this. Now there's an illusion that happens because when we draw, right, I say, well, I've got to draw my axes here, right? And so visually, you kind of see all of this, but then you also see this part of the x-axis, and that you can, in some sense, you can deceive yourself with your own drawing. Is that you see the risk there? Yeah.
Yeah, that makes sense.
Yeah, so that's what's going on there. Of course, the curve C is just the blue part there. If I can erase that, it's just the blue part. And so, yeah, it's not closed.
It just happens to also be 0, too.
Yeah, that's right.
Okay.
That's right. It's 0 for a different reason. And that brings me to one of my points that y'all have heard a million times. You're going to hear it a million more over the next few weeks here. And that is, it's not about the answer. It's about the reasoning, right? And so on a question like this, if you were to say right up here at the top, path independent, and this is a closed curve, and therefore the answer is 0, all that reasoning's wrong. And so even though numerically, I mean, the answer is the same, yeah, but the reasoning is just not valid. And so that wouldn't get any credit. So that's something you have to be really, really careful about. Always be very careful to interpret the question as written, right? Very carefully. And don't accidentally step on that landmine. Yeah, so great question. Thank you for that. All right. Okay, moving along. So yeah, how did I know that was a path-independent vector field? There is a powerful theorem right here. This is totally awesome right here if you want to know if a vector field is a gradient. And now, by the way, don't forget, we know gradient is path-independent and vice versa, right? But if you want to know if you have one of these special vector fields, this says all you got to do is compute Green's operator, see if you get identically 0, and if you do, simple computation, couple of partial derivatives. If you get flat 0, boom, yes, gradient, path independent. Just like we had up here, where I just took it as a given that this was path independent. That theorem that we were just looking at is how I knew this was going to be path independent. Okay, so how do we see this theorem? This is a sort of a multi-step little argument here. The first thing I want to do is point out we've already seen this part of the argument. We've already seen that gradients, and that means the same thing as being path independent as far as we're concerned, which means the same thing as all closed line integrals are zero. That was our first thing today, that those three things are the same. So now, how do I connect these two statements? These two statements right here, how do I connect that when all closed line integrals are zero, all double integrals of Green's operator must be zero? And that is straight up Green's theorem. So specifically, Green's theorem tells us exactly that closed line integrals, of course, a closed curve is a boundary of whatever region's on the inside. Closed line integrals are double integrals of Green's operator. That is exactly Green's theorem. So the idea that all closed line integrals would be zero, by making this connection, means that all double integrals of Green's operator must be zero. And now we're basically done at this point. I just have one last little conclusion that I have to draw. And that is, why are these two statements the same? And this is just going to be a sort of a hand-waving appeal, but I think this is very believable. What functions can you think of as integrands here? So I'm thinking about, Green's operator of our vector field in particular. What could this function in purple possibly be that has the feature that all double integrals for every domain, no matter what domain you look at, all double integrals are always zero? And I pose that, well, yeah, as long as we're talking about continuous functions, which again we are, the only way to do that is if that function is itself zero, and vice versa. So that's the argument. It's very clever, I think. This is the nice punchline. If you want to know, am I dealing with a gradient, aka a path-independent vector field? Here's how you decide. You compute Green's operator. You see if you get zero. If you do, yes. If you don't, no. All right. Now, before I give you a couple of examples, you know what? I got ahead of myself. One other thing I want to say about this. I want to talk about how we would describe a vector field that has this property. What name would we give to a vector field for which Green's operator is zero? I think there's a pretty natural choice here. Keep in mind that Green's operator, what it does, it should be in green, of course. Silly me. Green's operator, what it does is it's measuring the extent to which there's a kind of a rotation in the fluid. That's what Green's operator does. Green's operator is circulation density. It's directly proportional to how much circulation is happening in a little small region, right? So Green's operator is measuring how much the fluid has a rotation, and so that being zero means that there is no rotational aspect to the fluid, and thus the term irrotational. So you're going to hear that word from time to time, and just keep in mind that this is just a terminological convenience for saying Green's operator is equal to zero, which for the category of vector fields we're talking about means path independent. It means it's a gradient. To my continued frustration, it also means we can use the word conservative, right? So we have all these different words that all are talking about the exact same vector fields: conservative, gradient, path independent, and now irrotational. They're all the same vector fields. Different properties of all the same vector fields. Okay. All right, so so now this theorem that we just saw, this is a two-dimensional theorem. Notice that this is specifically in R2. There is a three-dimensional version of this theorem as well. The three-dimensional version of this theorem has us look at curl instead of Green's operator. And there's great reason for this. It actually is proved in a way that's morally equivalent to what I just showed you here. It's just that we don't yet have the three-dimensional version of Green's theorem that we're going to need to make that argument. So I'm just going to state this as a fact for the moment, and we'll come back and talk about the argument in a few days. But again, it's going to kind of just use a three-dimensional version of Green's theorem. Okay, let's do a couple of examples. Here is a vector field. At a quick glance, I have no earthly clue if that's a gradient of something, right? You could sit there and try to strategize, right? Try to come up with something whose gradient might be this, and eventually we're going to see that there is a way down that road, right? But we're not ready for that just quite yet. So is it a gradient? And I'm going to resolve the matter by using that theorem that we just talked about. I'm going to take the curl. I'm going to ask, is this 0? And if it is, I'm going to declare victory. And if it's not, then I'm going to declare defeat. So we take the curl. And as you go through and take the curl, there's a first coordinate. There's also going to be a second coordinate and a third coordinate. But check this out. You don't even have to compute the second and third coordinates of the curl, because all we care about is whether or not the curl is 0. Right? That's what our theorem up here says. Is the curl 0? 0 vector. Namely 0 in all three coordinates. So is this vector field 0 in all three coordinates? Well, apparently not. It's already failed with the first coordinate, right? So game over. Not 0 in the first coordinate means definitely not 0 as a vector. And so therefore this is not a gradient. Therefore it is not path independent, and you cannot play fun games by switching curves and stuff like that. Okay. All right, now here's another example. This is a two-dimensional example. So how about that vector field? Is that vector field path independent? And again, you can try to get clever and think, dream up some thing whose gradient would be exactly this, some anti-gradient, again, as I like to call them. It's hard to dream up what that might be. But you can just come at it very directly by computing Green's operator. You get 2. That's an easy calculation. 2 is clearly not 0, and so this is not a gradient. All right? Everybody happy? Okay. Now, I like this second example in particular because this second example is, I'm going to say the answer is actually pretty relatable. So we can draw a picture of this vector field pretty easily. In fact, we have previously seen this vector field. That's what that vector field looks like. And let's try to visualize a scenario in which this vector field is a gradient. And don't forget, gradient vectors always point uphill, right? So is it possible that these vectors could all point uphill? Well, of course not, because then as I go around, uphill, 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 uphill the whole way around, I've been going uphill the whole way, but I'm back to where I started. And that's not possible. It's basically just a sort of a equivalent to the idea of Escher stairs. So here's another nice way to think about what we're saying here with this picture in mind. You see that what we are looking at is a circulation, right? This is a fluid. This vector field would represent a fluid that's circulating, and that's what's not possible when you're not talking about a gradient. So another way to say this is that non-path independent vector fields cannot circulate. Does that make sense? Okay. All right. Okay, so let's see here. Yeah, right. Okay, so this little bit in the notes here, I'm going to pull up another one of my little PDF markup apps here. Oh, which one? Yeah, here we go. Okay, give me just a second to pull. I intended to do this before class started, and then I forgot. Where is it? Here it is. So what I have here is just an easier to see version of the diagram that you're looking at in the lecture notes. This file that I like to look at, by the way, is also on the website. You can download this at your leisure. It's just a little bit more spread out, and it's easier to do that when you have the advantage of typesetting. Right? So what is going on with this diagram? This is a little bit of a weird conversation. I've mentioned before that all of the theorems that we're seeing in this Chapter 6 and Chapter 7, what we call the vector calculus part of this course, all of these theorems, a lot of these theorems anyway, are actually kind of the same theorem. They're special cases, different special cases of the same theorem. This same theorem, unfortunately, being a much more sophisticated thing that we just can't talk about reasonably, I think, in this course. So what I've got here is kind of I've taken the ideas necessary to give a full discussion of the big theorem. I've boiled off all the formality and rigor and scary. And what I'm leaving is only the underlying sort of structure, just the punchlines for how does this pertain to me as I'm doing vector calculus in 2 dimensions. And so notice again now this is specific to 2 dimensions only. There's a 3-dimensional version of this down here. We'll talk about that at a later time. So this is, therefore, there's a tremendous amount of formality and sophistication and power that this diagram came from. And I'm not going to be able to make any of this precise, but you don't have to make it precise to be able to take advantage of the structure that this gives us. Exactly why we lay things out this way, you don't need to worry about. What you can capitalize on is the fact that if you choose to lay things out this way, amazingly convenient things will happen. And so I want to walk you through some of the really nice things that happen here. Notice that what I have this composition. And you remember long ago, back in Chapter 3, I made this assertion that if you compose gradient with Green's operator, good things happen. And I was very nebulous about exactly what good that was going to be. Right? Well, here we are. Gradient followed by Green's operator. And now let me also point out that I'm talking about boundaries here on this next line, and I appeal to your geometric intuition. If you have a 2-dimensional region, the boundary is a 1-dimensional curve. That's how boundaries work. Right? And if I take a curve and talk about its boundary, well, you get a couple of points. Right? So think of boundary as an operator that sort of moves you to the left, and then we have these operators up here that kind of move us to the right. Okay. So with all of that noted, and with the understanding that what we're going to do with points is we're going to plug them into functions. What we're going to do with, let's see here, I learned like this. What am I going to do with a vector field and a curve? I'm going to compute vector line integrals. And what else would I do with a vector field and a curve? And what am I going to do with a function on a 2-dimensional region? Well, I'm going to compute double integrals. Okay. So with that layout, let's just kind of talk through what does the fundamental theorem of line integrals, what does that look like on this diagram? The fundamental theorem of line integrals says that if I have some function and if I look at its gradient, and if I take some curve and look at its boundary points, then if I do this kind of an evaluation of that function on those boundary points, in other words, like so, versus if I do this kind of an evaluation of that gradient on my original curve, like so, then I get the same thing. So the fundamental theorem of line integrals could, again, with the understanding that I want to sort of track how things are moving in the context of this diagram, the fundamental theorem of line integrals kind of says that when you push to the right and you push to the left in this part of the diagram, the resulting calculations are the same. Which doesn't tell us anything. This is not a meaningful punchline. I just want to point out that's how the theorem lays out on the diagram here. Okay, so now let's do the same thing with Green's theorem. Green's theorem says if I have a vector field and if I look at Green's operator, and if I have a two-dimensional domain and I look at its boundary curve, Green's theorem tells me that a line integral of my original vector field on the boundary curve and a double integral of Green's operator on my original domain are the same. In other words, it lays out on the page exactly the same way, going to the right, going to the left, evaluating accordingly. You get the same thing on both sides. So this is, I think, a real kind of, I like to call it an eyebrow raiser, right? Like, wait, what? How could... These are totally different theorems, and yet they lay out on this diagram identically. Did everybody see that? That's weird. Pretty surprising. And just to give you a little bit of foreshadowing, this pattern, this connection, this odd connection that we see between the fundamental theorem of line integrals and Green's theorem, we're going to find that the same thing happens with Stokes' curl theorem, and the same thing's going to happen with Gauss's divergence theorem. All of these theorems have the same pattern on this diagram. Ultimately, the reason why is because they are all the same theorem. Right? And again, how to make that precise is not something we're going to be able to deal with. What we're going to be able to benefit from, though, is that really, with all of these theorems, you just need to understand the pattern. Right? If you let this diagram sort of be your bookkeeping system, how you sort these ideas in your mind. Right? If you think of gradient and Green's operator as composing like this, then the sort of pattern that helps you understand that theorem is the same as the pattern that helps you understand that theorem, which is the same as the pattern that helps you understand all the other theorems. So tremendously valuable, right? If you want to cut your comprehension load by a big factor, right? Organize these ideas in the way that I have laid out on this diagram, and things will just kind of magically fit together and make sense and work out. It's really, really handy. Okay. All right, let's see here. Last thing. Well, you know what? I'm not going to be able to... Okay, let me do a different last thing. I'm not going to be able to finish 6-3 today, it looks like. I just want to point out one other last thing, and that is that there are certain special vector fields we've talked about. Recall from earlier in today's lecture, we talked about gradients. Vector fields that are gradients of some function that I like to call an anti-gradient, as you may recall. That these are the same as vector fields for which Green's operator is 0. Right? So exact same vector fields. The ones that you get from being a gradient are exactly the same as the ones for which Green's operator is 0, which are still, in fact, exactly the same as the vector fields that are path independent. And the way I like to represent path independence is that if you have two curves that give you the same boundary points, then you get the same value for the line integral. So this is a kind of a little, I'm going to say, a pattern on this diagram. And this pattern on this diagram, and this is just pure foreshadowing, this pattern that we've seen here is going to likewise show up in 3 dimensions, and it is likewise going to show up 1 dimension over for higher dimensional analogous ideas also in 3 dimensions. And so what we're seeing is sort of a tip of the iceberg. If you notice the pattern in this context, that same pattern will pay off in the future. Y'all have a good rest of your Wednesday. See you later. Pick up here next time.